Recording is on.
Hello everyone that's joining. Stephan, as it's a couple of minutes to, at 12, I'll announce that you're going to be the presenter, and then you can start to go through your slides. Okay.
Yes, great, thanks.
Brilliant, thank you. Hi Skylar. Hi Mike. Hi Miklos. Hi Pranam, Path, Michael, Mike, JL, Gorkay. Hello everyone.
Hello.
Hello.
Okay, we'll just give another 2 minutes, 1 to 2 minutes for people to arrive, and then we shall start.
Okay.
Okay, everybody, let's make a start. So, welcome to the tea time trainings this afternoon. Today's presenter is going to be Stephan, and he's going to be talking about, and the topic is how to use assertions properly. Just a reminder that the session is being recorded and will be available on our YouTube channel. So, Stephan, over to you.
Yes, thank you. Hi, everyone. So assertions, I'll do a quick run through of some aspects on them. First, go into some more abstract ideas about them, and then some technicalities of how to use them in our C++ code mainly. But the first part should even be for other languages as well, for their ideas of how to assert something or how to use assertions. So what's an assertion? It's stating a fact about the program, how its state is, or how the programmer thinks its state should be at a given point while executing the program. So this is about the runtime of the program, not about the static shape of the code. And to be useful, they of course should be stating non-obvious facts. So you don't state that when you have a variable and assign 1 to it, that variable then has a value of 1, because that's obvious. What you want to assert is about things that are, for the casual reader at least, non-obvious. So the main point for having assertions is to guide the reader of the code who maintains the code, who makes changes, and then needs to make sure that these assertions still hold, that you claim hold, or to make sure that if you add new code, then you don't violate these assertions, which is the same as I said before. Sorry. It's not only for the reader, of course, but what we want to get out of this is also that it is beneficial even for the end user in some way. And how we get there, we'll get to that. So restating assertions, kind of a command on something, a way of describing in the code for the reader, this is something relevant about the program state at this point in the program flow. So how do we do that? Or what kinds of assertions do we have that we want to do this with? One example is class invariance. And now one way to do this is to just write a command somewhere. And if you look at this command, it already seems to if there's some comments on something, just shout and step in, by the way. So this already seems to violate what I wrote on the previous slide at a given point in the program flow, because this is a command written at these member variables, which has nothing to do with program flow, of course. But there's all these public non-const member functions that you see samples of here. And the idea here is that these class invariants shall, of course, always hold when one of these functions is entered and when one of these functions is left. So these should not, while modifying the state of such a class instance, by modifying the state of the program, that is, should not start to violate these assertions that are apparently useful. For example, the skip front should probably not skip so many elements that it goes past the original length of this thing. It presumably just changes the length member, data member, and should not make the invariant break. So how does such a function do that, which leads us to the next set of assertions or places where we put assertions. And that's a rather big one. That's the preconditions of functions. So when you write a function, you have in mind what the actual arguments that you pass into it can actually be. And everybody who uses your function needs to make sure that they pass in actual arguments then that satisfy these assumptions, because otherwise will be broken and thinks that the function is not, the implementation of the function is not designed to handle, will then start to cause crashes and undefined behavior and whatnot. So the usual way is to specify some preconditions for your functions. And again, the first way is to do this with a command. Like the first function needs to have a non-null pointer passed in. The next one needs to have a prime number for whatever odd reason. And the third one wants to have a zero terminated byte string, so the usual C string. So this must not be a null pointer, must point to some actual block of memory that is accessible to the process, and must, when you read through it, you must get to a null byte eventually and not fall off the end of the memory block or something. And we'll come to how you actually want to enforce these later. First of all, it's just commands that state things about your program. Another thing is post conditions, like in the example with the invariants. We want to have the preconditions apply when these functions are called, and as a post condition, also this invariant shall always hold. This is kind of implicit here, and you can also have explicit post conditions. And again, you first of all write them down as some kind of command. So like this way of reading some bytes from somewhere into some array, and you state that whenever it returns true, which presumably means there's no error having occurred, then you'll have at least read one byte, and this len will then receive that number. And beyond those preconditions and postconditions, you also have conditions and assertions about the non-obvious facts in your program. This is where the usual idea of where you would add an assertion or an assert statement probably kicks in. This is like, we call this read non-empty from the previous slide. It returns true, so we are in the if true branch here. So we know it read at least one byte. So we know that we can access the array element 0, and it will have a valid value now. It will not be uninitialized, because the post condition of that function was that it returns the non-zero number of bytes read. So this is a bit of a subtle thing to know here. When read non-empty returned, it'll not only assign to len the number of bytes that it did read, but it actually did read more than 0 bytes. So kind of a non-obvious fact here is that when read non-empty returned true, that array element 0 has been initialized here. So we state that with an assertion, again, with a command. Another thing is about reachability, where you often have often want to give the reader a clue that yes, this place will be reached. So you have some very odd function that just returns a number, and you have no idea how this function is implemented. And for whatever odd reason, to make a short example, here is the reason in this case, you call that function in a loop until it returns 0, and then you break out of that loop. If you don't know about this function, then you won't know whether this loop will ever return, whether the mutex unlock past that function, past that loop will ever be reached. So if you look at the code, at just this code without its context, you might wonder, is this even safe? Will we ever unlock that mutex, or will this go on forever and keep the mutex locked for any other threads? Well, the strange random function does have an assertion here, a post-condition assertion. It'll eventually return 0 when you call it often enough. So the supple fact that we state here with the guaranteed to be reached command assertion at the bottom is that yes, because of how the strange random function is actually implemented, we are guaranteed to reach this at some point in time. What is, for practical reasons, more often of interest is the opposite, the unreachability of a point, which often arises if, for example, you have a function that takes an enum and for each of the enum values returns something. If you have an exhaustive switch case there, then you're sure you can never reach the default branch or fall out of the switch at all. So you don't need to invent a return value here that you'll never pass out anyway, because you'll never reach that point at the bottom. So instead of having some nonsensical return 0 or return -1 for the default case, it's nicer and better and more predictable and more robust in the overall if you just can assert this point cannot be reached. So that's another common reason to use assertions. Now, assertions as an abstract idea stating facts. What is a violated assertion then? Well, it is the situation that you state at this point in the program P must hold, or a condition must hold. If it doesn't, then there must be an error somewhere. Not a user interaction error, not a disk full error, but some logic, some programming error that you made or some other person changing the code made somewhere, or even somebody who wrote the underlying operating system or whatever part of the stack that you are using made. And that's the error being made need not be at this point where the assertion no longer holds, or it can be at an earlier point as well. You just now notice that at some point you left your space of well-defined program state and wandered off into something is broken. Typically, there's a real error somewhere. It might, of course, also be that the assertion itself that you wrote down was nonsense to begin with. So there's also always this a chance that whatever assertion you wrote down, you shouldn't have written down in that way and should have been more careful with that. But anyway, you relied, when you wrote down that assertion, you relied on it being correct and you made assumptions based on that. And now you find out that this assertion wasn't working because you wrote something silly, something stupid as the assertion, but still all the code that you then wrote, assuming that that assumption must hold, is broken now as well. So whether somewhere else in the code there's a bug or whether the assertion itself is buggy, doesn't matter. We've left the space of well-defined program state now, and all bets are off. So we don't know what state our program is in, because it's no longer in the space of the states that are valid. So we can't do much about this anymore. So what should we do? On the first slide, I said we want to have this for the benefit of the end user as well. So it would be great if we don't have these assertions only as commands, but as something actionable. And if an assertion fails, then we want to do something. Question is, what do we want to do? The first idea might be for something like a precondition. If it doesn't hold, we just chicken out and exit that function quickly. But that's of course nonsense, because all bets are off. We don't know what state our program is in anymore because it's not in a well-defined state. So we carry on. We avoided a null pointer dereference maybe in this function. Hooray, a crashed user sample is fixed with that. But the program is in a state we have no idea about, and we'll just get to further bugs down the road, or the program becomes non-responsive or doesn't do what it should do because we just don't execute this function anymore, whatever important things it would have done. So this is a very bad idea and obviously not what we want to do. Second idea, we throw some exception. There's even these logic error exceptions defined in C++ for, probably not very, or sometimes useful, sometimes unuseful reasons. Because what happens now, if we check whether we have a null pointer and then throw an invalid argument exception, well, that means that the function's precondition or assertion is no longer what the function actually does. The function is now of the kind, give me any pointer, and if it's a null pointer, I will throw a standard invalid argument exception or any kind of exception. I'll return with an exception. If it's not a null pointer, I'll do what I'm originally asked to do. So this changes the function to something completely different. And now all the places in the code that can call this function can now happily call this with a null pointer as well. But what they also need to do is take care of what the function returns, which can either be returned normally or return abruptly with an exception. So all the places in the code that call this function must now be prepared to either know they cannot get an exception because they know that they don't pass in a null pointer, or they might get an exception. So this is a completely different function now. Functions like this are useful, for example, for libraries or for LibreOffice extension model, where you can write extensions that call into the core code. It might well make sense that at the layer where the user code meets the core code, you check for these kinds of things so that a user error, an error in a basic script that a user writes doesn't lead to a null pointer segmentation violation down the road in the core code. But for the core code itself, for functions in the core code itself, where we know who calls these functions and we can mandate that these functions must never be called with null pointers, it's more ergonomic to have functions that just have a stated precondition, must not be called with a null pointer, and then a violation of that should not lead to an exception being thrown, because this is then a different kind of function. So what's the right thing, of course, is to just abort the process at this point because all bets are off. We don't know how to proceed. Everything that we would do would just lead to more corruption in the worst case. So just shut down the process and be done with it. And that's what the C and C++ assert macro, of course, does. So all this building up to here was just introducing this good old macro. All the places where we have these commands until now, we should probably use these assert macros instead because they exactly do what we want to achieve. And that's what you usually do. For example, back to these functions and their preconditions. So the first function doesn't want a null pointer, has the precondition must be non-null. So we can start off the function with an assert that p must not be a null pointer. The second one wanted a prime number. We happen to have some function maybe that returns true if some number is prime. That might be a bit expensive to call. So that's where the idea of this ndebug thing comes from. Having the asserts enabled all the time would be great because they find errors in our program. Even in production, they find errors in our program and then kill the program early before it can do more nonsense. So having assertions enabled or having assertions kill the program is a useful thing even in production. But some of these assertions, like we see here, can be expensive to evaluate. So there's a trade-off. So there's the ndebug macro, the ndebug flag that tells the standard assert to just ignore its argument and don't evaluate it, so that we no longer notice if we have an error, which is an unfortunate thing, but a trade-off. And then there's function f3, which wants its argument to point to a ZTBS, to some zero-terminated byte string. So how would we check for that? Well, we can check the first thing that it's not a null pointer, but how do we check that it actually points to an array of memory that is accessible and that if we iterate through it, we eventually reach a null byte? Turns out we can't, because if we would access the memory, then we would run into undefined behavior. So we cannot specify in C, in C++, an assertion here that checks whether this is actually this assertion actually holds. So we must live with just the command here. So there's often the case that either for this case or for the performance case in the is prime example before, that you don't specify something as an actual assert macro use, but just specify assert something via the good old command. And for the other often occurring case of this unreachability, you often see these assert false in your code across a code base. And these are also often used by static analysis tools to see the programmer did assert there that this is unreachable, so I wouldn't bother to emit some warning that you don't have a default in your switch, or that maybe if it's even not exhaustive, the cases, because the function, this f function, has a precondition that it can only be called with E1 to E3, and there's also an E4. The static analysis tool would know this and would warn then that you didn't handle the E4, which you don't need to handle because it cannot be passed in. but you can then tell it, I can't reach this place here. So often these tools then are smart enough to no longer emit their bogus warnings or their false warnings. So this was the useful uses of the assert macro. As a corollary, the not useful ways of using it is once I used an assert to state that this cannot happen, that this must not happen, that if this happens, I'm out of my well-defined program space, then it doesn't make sense to have an assert followed by something that checks for the same condition and then does something. So there's never a reason, like we've seen before on the other slide, this defensive programming disaster or pseudo-defensive programming disaster, just returning null here or just returning here if it's null. It doesn't get any better if you precede that with an assert, because your program is out of its mind now. It's doing some. It reached a point where it's no longer doing something useful. So how would you then continue with a return there if it is already in the state where it's not doing anything useful? So never do that. So if you use this assert macro, it's a pain to use for a couple reasons. One is that if you have this ndebug defined, so that assert is just ignoring its argument, then you often enough run into cases where you have some variable that you only have for the purpose of checking it in this assert, and otherwise it's unused. So then when you do build with the ndebug in the ndebug mode, then the compiler will complain that some variable is unused. So you need to dress that up either with this maybe unused thing or casting it to void or whatever was the old ways of doing that. Another interesting thing with the ndebug is if you have some assert in some include file in an inline function, then if one part of the program is compiled with ndebug on and the other is compiled with ndebug off, then you effectively have two versions of your function, of your inline function. One that includes the code to check and abort, and the other that doesn't. And that's clearly a one definition rule violation here, because each inline function must be defined exactly the same in each translation unit. So the net point to get out of this is don't build part of your program with ndebug and part without. That usually doesn't work. And last thing is, if you just look at the assert in the standard, it explains that if ndebug is defined, it just ignores its argument, and otherwise it evaluates its argument. And if it contextually converted to bool is false, then it's called standard abort. It doesn't give all these abstract philosophical ideas of what assertions is that we build up prior. So if you then get into an argument with some developer who says, but I want to, in debug builds, I want to get the information where this pointer is null, where I'm doing a mistake. And in production builds, I just want to carry on because carrying on is harmless in this case. Then you have a hard time arguing with these people, because if you just look at the mechanical semantics, call it, of the assert macro, then they might have a point with that. But if you look at the philosophical idea behind asserting some fact, then they don't have that point. So it's a bit can be a bit problematic to discuss with people who only look at this, let's call it mechanical semantics of it. And especially the first two of these issues here have led to the standard going further with better things than this good old assert macro. And the first thing that came along was the in C++23 the standard unreachable, which is a bit of a, it looks like a function. It's defined as a function in the standard library, but it's a bit of an unusual kind of function because what it does is tell the compiler, yeah, this point can never be reached. And it's just the replacement for this assert false. We saw a few slides prior. This one, the assert false there is now better written as a standard unreachable because it also gives the compiler an idea that this is, it can't reach here and it doesn't need to glean that from the somewhat more vague assert false thing. And in LibreOffice code, we have this O3TL unreachable macro because we are not yet C++23 there. But once we are, this can go, and it's just a wraparound standard unreachable for now. Going forward into C++26, which is work in progress at the moment, we might get even more stuff there. So this is this contracts thing. This is brewing for quite a while now. They voted a version of it into the draft of C++26, but turns out they're also unhappy with it. So it might also go out of it again. I don't know. But the idea is that one part of is that we have a new syntax to write pre and post conditions. So that's at the top here. So instead of adding an assert at the top of the program, of the function, that n must be greater than 0 and less than 100, say, we can have this new syntax with this pre thing. For the preconditions, we have a post for the post conditions, and the return value, you need to invent some name for this here so that you can actually use it in your condition. And this is the R here. So return value, when the value we passed in is 0, it will also be 0. Otherwise, it'll be greater than 0. And so that we can actually reference the arguments, the input arguments at the post condition. We now need to make these parameters of const type. So this is why we have this odd and somewhat ugly in const n here at the top. The most interesting part maybe of all this is that there's not only this pre and post, but also a new keyword contract assert, which acts somewhat like the existing assert macro, but wouldn't have its drawbacks, or wouldn't at least not have this drawback that if ndebug is defined, that then we ignore this argument. So there's no chance if you use a variable only in a contract assert that the compiler would warn that it is otherwise unused, because it will always be seen by the compiler. It wouldn't necessarily be evaluated. So this is the these contracts would still have these various modes of compilation, what you would do when a contract is violated. And that's also where the issues come in. So they found out they would still run into this ODR violations and stuff. And that's why this whole contracts thing is a bit of a not safe bet whether it will actually land in C++26. But on the horizon is definitely something that replaces the old assert macro with something that is more ergonomic to use. And to finish off, there's also some related things that are not exactly assertions as we defined them at the start. One example is this static assert, of course, which is in since quite a while, C++11, which is not about facts while you execute your program, but it's rather about facts that the compiler can check at compile time. Like if you have a buffer that is large enough to assign or to create an int into that buffer, you can do that with a static assert check. You all probably know. And of course, as I said, it's unrelated to any point of execution in your program, so it wouldn't ever work. This unreachable thing to do that with a static assert, because when the compiler sees this, it doesn't evaluate, it doesn't execute the function to only static assert if it would fall out of the function and not have done a return before that. But it just reads the source code, sees there's a static assertion, evaluates it at compile time, it's false, it will always terminate your compilation with an error. So that's not the way to use it, of course. Which if the condition is a bit more complex, you might occasionally get drawn into thinking, oh, this is some useful place for a static assert until you, especially in templates and stuff like that, until you then find out, oh no, this is nonsense, and always stops compilation. What's also new in C++23, so we don't use it at all yet, and probably don't have that much of use for it either. And it was also already present as some compiler-specific extensions in some syntactic form others. So the Microsoft compiler, for example, had that for quite a long time now, this assume thing. It's kind of orthogonal to the assert. It tells the compiler that it can make some assumption, and that might allow the compiler to optimize things. For example, in this very cheesy example here, just for the sake of an example, you have a function that divides an integer by 2. And if you know that the value will never be negative and your instruction set, CPU instruction set, has a logical right shift instruction that is probably less expensive than an actual division instruction, then you can use that and don't need to bother about a sign bit being replaced by 0 now, because you only have positive values here. So this is a place where it might be useful to have this assume, to tell the compiler something that is non-obvious. And often enough, you would then also need to assert that your assumption is actually true, because what you don't want to have is that you tell this compiler some assumption that isn't actually right. So it's usually both of them. And the compiler, with the assert macro at least, of course, the compiler can draw any conclusions from that, because if you build with ndebug, then it'll just be ignored, whatever you write there. So this is why compilers typically don't draw such assumptions from the assertions. And for the to be introduced contract assert thing, it's even by design that the compiler doesn't draw assumptions, optimizations assumptions from that. Right, that's about it, I think, from my side. So I hope you have lots of questions. I see you already dumped tons of questions here. Let's see. Mike, if you can't reasonably handle the input, it's not a programming error, right? Yes, of course. So
it was about the erroneous assertions, which could, of course, show how I made a mistake, but it still documents what I assumed and so helped to fix it, which was my idea.
Not sure I get you now, but sure, if there's something like you're getting some value from somewhere outside the scope of your program, then you shouldn't assert that this value will be in the range 1 to 5, because you can't, that's nothing you can assert as a fact about your program, because it depends on what you get as input. Right.
Let me immediately explain what I meant by my next comment. It was when you described that we shouldn't write assert and immediately check for the same thing. And I wrote that this is exactly what happens in lots of our actual functions implementations.
Yeah, that's true. Because I think this is I think there's multiple points to that. For one, the use of asserts or OSL assert macros and whatnot traditionally has been muddy waters in a way, and people added them without really knowing what they should do. So that's where also this idea of getting rid of these old OSL assert and whatnot stuff, and replacing them with these sal warn and sal info and whatnot things came from, to get to a new clean slate. And but yes, there's also probably, for one, there's old uses of assert that should not have been asserts. There's old uses of assert, or there's uses of asserts followed by actual code that does something if the assert is false. And in cases I'm aware of, this has always been this argument there. This is something that should not happen. I'm pretty sure it should never happen, I as the author of this code, but I'm not 100% sure. And so what I want to get out of this is carry on, because or do something, or not carry on and do something special here for production builds, but not be silent about that for debug builds. And I want to get a handle on this, if my assumption was right, that this assertion is right. So I'll stick an assert in here. But this, of course, only shows the cluelessness, or let's call it the helplessness of the person writing the code there. So it's kind of an engineering trade-off, to be honest and say, I have no idea what this code's conditions actually are. So I'll try to get the help of the mechanical semantics of the assert macro here, to give me an abort in debug builds, if this is not true. Maybe it would be better to be more explicit in such cases and not use the assert macro there, but use an explicit if condition is false, then standard abort, and wrap that in if not defined any bug or something to make it only hit in debug builds. Because it's not the programmer with certainty stating their assertion, that they know for a fact that this is a fact about the program state, but they being helpless there and trying to get a grip on what the code actually does. And that's not something that the assert is for. search should always be used with confidence. That's it. Does that maybe explain a bit? Probably. Are C++26 contracts better in some way? Do you know what upside they provide? Yeah, so they're better in the way of what I said about the contract assert versus the assert macro and the unused variables. And they also make it more, with the post conditions, maybe they even make it easier to write that code for the post conditions. But in the end, they build on this, or at least in the current draft, they build on this idea of having a more varied way of responding to failed assertions or failed condition contracts there. But as I said, this is still a work in progress. I'm not yet sure how it'll actually end up. So this is a bit of a vague thing at the moment. Just wanted to give it as an outlook into what might be coming. Sahil had something with int const n and will be a better syntax. Which slide was that, Sahil?
The contracts. So instead of adding pre and post, we mention it with the parameter declaration.
Yeah, maybe that would be a nicer syntax. So, but you can have lots of pre and post conditions. So maybe not. I don't know. This is what they came up with. So, and let's see what will actually end up in the standard. Quellen, so we can't replace likely with that, I presume. Yeah, I hope that sal likely doesn't even get used anyway. And the sal likely actually is there's a likely and unlikely annotations, or hot and cold. No, I think they're likely and unlikely in the standard. And there's a blog post about why you should never use them. So better not try to tell the compiler how to be smart and optimize stuff. It usually knows better how to do that itself. So sal likely, sal unlikely was a poor addition. And I guess you shouldn't use them. And I assume will not be of much of widespread use either. Maybe there's places where it does make sense if you after you measure your code for optimizations. But on average, I guess it's nothing that should excite us.
I find it a little bit, I don't know, extreme to say never. Clearly, if you have a function, a hot function, that has error handling that you know is extremely rare, you do want to tell the compiler that this condition is not important, and so it can outline it, it can move it out, it can optimize it for space rather than speed, and do the opposite for the hot path, which is the one you want it to be optimized for speed. You want it to be, direct one, not to have a jump before it is, you know what I
Most
mean?
of the time,
Like,
I think the compiler
certainly
can
there are places.
either figure it out itself or be guided by optimization.
Profiling.
If you profile guided optimization, yeah, thanks.
Sure.
So
By the way, if you do profile guided optimization, it ignores the likely and unlikely. So it's smart enough that it only uses it if you don't do profile guided runs.
yeah,
if
but
you did,
then
it ignores it.
But then they're probably of little value. because if you want to do profile guided optimization anyway, then just don't bother to write them. They just would load your code for no real value, I guess. But then also it's a bit of a sidetracking here to let's not get into the.
Yeah, fair enough. But it's worth
optimization.
adding that likely and unlikely is not a compiler optimization. It also adds a prefix to the jump instructions. So it is actually a hint to the processor. And it does make a difference. You can actually measure it. So.
Yes, of course, you can measure the difference between the instructions. Question is whether the compiler isn't smart enough to emit the right instruction in the first place. I think that's the bottom line. There was a nice blog post at some place, I can't remember now, which did have convincing arguments why you shouldn't be using at least the C++ likely, unlikely things. Don't know the details yet anymore. Yeah, I'll try to dig it out. And okay, the rest of this seems to be about likely and unlikely. So any further questions?
Stephan, should I go by and just ask people name by name that I can see on my
Sure.
screen? Yeah. Okay, so if anybody has any questions, I'm just going to call out your name and see. So I have Miklos Andrash Jayon.
Thanks for the presentation. It was really useful to see this new C++ since this contracts API is coming up, and I was not aware of that. So good to know that's the new thing to read up on. Thanks.
Okay.
So no question from me. Thanks.
Thanks, Andrash. Then I have Kerr, Ezene, Gorke, and Jayon. No. Then I have Michael, Parth, and Prenam.
Thanks, no questions.
Thank you. Then Balash and Timur.
No question, thanks, Stefan.
Thank you. Then I have Moet, Justin, Aaron, Attila, and that's it. Unless I've missed anyone. No.
No question.
I have a quick one. Thanks, Stefan. Good stuff. I wonder if you know the lowest compiler version that supports the pre and post contracts.
There is an experimental version of Clang. It's on Godbold, I think, where you can experiment with that, if I'm not mistaken.
So we don't have to wait until 26 is what I'm hoping for, right? Because if we did, then it would be probably 2027 before we can have the feature.
You can play around with that, and that one also has an additional compiler switch, which tries to avoid this ODR violation issue, where part of it would be compiled in one way, where these contract violations lead to one outcome or one behavior, and other parts of the program would be compiled with another flag, which would lead to another behavior, and then you would have ODR violations in your inline functions. So the person that implemented this for Clang came up with some additional compiler -f contract group, something where you can specify behavior for full groups of contracts, and then you need to I think you need to also have your contract asserts decorated with a contract group they're in or something like that. So can read up on that. And yes, there's
that's really interesting.
experimental versions of Clang, at least, that try to implement that.
Yeah, I imagine the ODR stuff is probably not going to play nice with mixed compiler usage, meaning if you have some object files compiled with GCC and some others with Clang, you're out of luck.
Yeah, probably as well. And I think there's at least parts of these contract specification relies on your standard library. So I'm not sure how well until now GCC and Clang. I mean, GCC, I'm not sure if they even have an implementation of it yet. Don't know how well they play together. Yeah, I guess
Fair enough.
To actually use it in our code, we'll have to wait for the final specification in 26 and then see what the compilers offer anyway, because as I said, they're not. So at the moment, there's pushback against, so they voted it into a standard draft earlier this year, and now they're starting to experiment with it and gathering pushback. So they might also get it out of the standard again before it's final. Let's see.
Yep. Thank you. Thank you.
Thank you.
And that was everybody on my screen, Stephan.
Okay, then thank you all for listening and see you next week.
Thank you so much. Thanks, everybody. See you next week.
Thank
Bye.
you. Bye.
Bye-bye.
Bye.